Welcome to our Quantum Deep Dive. Today we're embarking on an in-depth exploration of a really pivotal figure in modern quantum research, Hartmut Neven. Our insights for this discussion, they're drawn from a fascinating essay by Yorgo Schneepat. Now, Neven, he isn't just someone who watched the rise of quantum computing and AI. No, he actively, forged the connection between them.
Yeah.
Sparking innovations that are fundamentally reshaping our tech landscape.
Exactly. And that interdisciplinary vision, that's precisely why his work is so important for you to understand. Neven's unique background, physics, informatics, machine learning, it gave him this singular ability, an ability to translate incredibly complex theoretical ideas into groundbreaking actual technologies. He hit milestones that truly push the boundaries of what computers can do. It makes him indispensable, really, as we go deeper into this new era.
Okay, right. Let's unpack this journey then. Who is Hartmut Neven at his core? What were those early influences? We can trace his story back, from a childhood curiosity that really blossomed into an incredibly rich academic career. Born in Germany, showed an exceptional gift, apparently, for mathematics and natural sciences from a remarkably young age. And he wasn't just, interested in science. He was deeply inspired by giants like Albert Einstein and Werner Heisenberg. So it seems pretty clear that this early fascination with theoretical physics, plus this drive to connect abstract concepts with real tech, well, that was a foundational thread.
Oh, absolutely. That thread defined his whole academic path. He pursued studies in physics and informatics at top universities, German and international ones, always driven by this clear goal, translate theory into practice. And early on, his interest naturally went towards computer vision.
Right. Teaching machines to see.
Exactly, making them automatically interpret images, videos, and even back then he had this, almost prescient foresight about quantum principles, how they might just fundamentally transform computing. His PhD in informatics, that really cemented this link between machine learning and computer vision. His research, it involved developing algorithms so machines could analyze visual data, basically building sophisticated mathematical models. Think about linear regression, for instance. It's a way to find a straight line relationship between data points, like the computer trying to learn how to recognize an object, let's call that Y, by looking at pixel values, the X's. His work helped build those predictive links, making visual analysis really robust.
And these weren't just, dusty academic exercises. His early research successes, his publications, they quickly got noticed. His innovative way of combining machine learning and image processing was genuinely novel then, and it really laid the essential groundwork for his future, his career in tech. So here's where the story takes a really pivotal turn, right? After all this impressive academic work, he decides to join Google. A company already known for relentless innovation. He found the perfect platform there, didn't he?
He really did. A platform to scale up his work in AI and pattern recognition massively. And one of his most significant contributions there quickly became known as the Neven algorithm.
Yeah.
This was a major step forward, rooted in sophisticated machine learning, statistical analysis, engineered specifically to efficiently analyze visual data. It was all about getting machines to see and understand content in a much more nuanced way than before. To give you a bit more technical insight, the algorithm used advanced mathematical techniques for pattern recognition, classification. Think of it like finding the absolute best way for a machine to fit a model to what it's seeing, pixels, other visual info. By optimizing these models, the algorithm could achieve really robust, accurate object recognition, even in messy real-world situations.
And the impact wasn't subtle, was it? It was immediate, far-reaching. It proved to be significantly more precise, more efficient than older methods, which made it perfect for real-world stuff, especially on devices maybe without huge computing power, like the smartphone you might be holding. It got integrated pretty swiftly into various Google products, boosting their capabilities quite profoundly.
Yeah, like Google Lens, a concrete example.
Yeah.
Lots of people use, maybe without thinking about the tech behind it. Point your phone, it identifies objects, translates text, scans barcodes, all in real time. That directly shows the practical power of this Neven algorithm. Science into everyday tools.
Absolutely. And what's really fascinating is how Neven's expertise here in machine learning, pattern recognition, how it naturally led him towards quantum research. His background in things like optimization, linear algebra, probability foundational for classical AI, it turned out to be incredibly relevant to quantum informatics.
So the skills transferred. Exactly. His key insight was realizing quantum computers and AI weren't these separate, distant fields, but rather they were complementary forces. They could actually enhance each other in really powerful ways. And that understanding directly led him to establish and then lead the Google Quantum AI team.
Right. So this bridge building, What did it actually mean for the future of computing? What achievements came out of it? Well, under Neven's leadership, Google Quantum AI set off on this incredibly ambitious mission, developing quantum computers capable of tackling problems that are just impossible for classical supercomputers, even the biggest ones. We're talking challenges like simulating complex chemical reactions perfectly, or optimizing huge, intricate global networks.
Problems where classical machines just hit a wall computationally. And they achieved one of the most significant breakthroughs with the Sycamore processor. This is a quantum computer built on 54 superconducting qubits. Now, a qubit...
Unlike a classical bit, right? 0 or 1.
Precisely. A qubit can be both at once superposition. And they can be linked entanglement. That's where the power comes from. But it's incredibly fragile. You need to maintain quantum coherence. Keep those states stable long enough to compute. Sycamore was engineered specifically to push those coherence boundaries.
Which brings us to that huge 2019 headline, Quantum Supremacy. Google's team, Neven leading, used Sycamore to do this complex calculation in just 200 seconds. And the comparison was staggering.
All right.
IBM Summit, the world's top supercomputer then, would have needed an estimated 10,000 years.
Wow. Yeah, that number really grabs you. But it's important to clarify the nuance there. Quantum supremacy, it's often misunderstood.
Okay, what's the catch?
Well, it doesn't mean quantum computers suddenly beat classical ones at everything. Not at all. It specifically showed that for certain kinds of problems, like generating specific random patterns and checking their probabilities, a quantum computer could achieve this exponential speed up. It was a critical proof of concept. It showed quantum computing wasn't just theory. It was feasible. It could solve specific, previously out-of-reach problems. Signaled the dawn of a new era, really.
And Neven's approach wasn't just about the tech itself, right? He was big on collaboration.
Huge. He deeply believed in global, interdisciplinary teamwork. Under him, Google Quantum AI actively partnered with top institutions. University of California, Santa Barbara, for example, Max Planck Institute in Germany, fostering vital knowledge exchange, pooling talent from everywhere. That collaborative spirit was almost as important as the hardware.
A blueprint for progress, you could say.
Yeah, really.
Okay, let's shift focus slightly. Let's explore Neven's ongoing work, his long-term vision, and also the big questions his work raises. He's made major contributions to quantum algorithm development too, hasn't he?
Yes, things like variational quantum eigensolvers, VQEs.
DQEs. What are they good for?
They're hybrid quantum classical algorithms, really good for tasks like calculating molecular ground state energies, which is crucial if you want to discover new drugs or design advanced materials.
Okay, and there were others.
Right. Also, quantum approximate optimization algorithms, QAOA, those are tailored more for real-world optimization puzzles, logistics, supply chains, that kind of thing. And importantly, his work also pushed quantum error correction forward.
Which is essential, right, because qubits are so fragile.
Absolutely vital. Enhancing qubit stability, making quantum computers more reliable by tackling the noise that messes up calculations.
And you mentioned earlier this synergy between machine learning and quantum computing that he envisioned.
Yes, that's a really compelling part of his vision. He saw how quantum computers could drastically speed up certain heavy-duty parts of machine learning, like training complex models faster or analyzing truly massive data sets. But conversely, he also saw that AI methods could actually help optimize quantum algorithms, make them better, reduce errors in the quantum computations.
They help each other.
Exactly. A virtuous cycle. Quantum neural networks are a prime example of where this combination is starting to show real promise.
And this combined power. What kind of unsolvable problems are we talking about tackling?
Well, imagine doing incredibly detailed simulations of molecules that could revolutionize drug development, or accurately predicting material properties to create, say, far more efficient batteries. These are problems needing exponential calculations, things that currently only quantum mechanics, maybe boosted by AI, seems capable of handling.
That potential is just immense. But it must bring challenges, too. Ethical ones.
It definitely does. And these are critical ethical and societal issues that Neven himself has openly talked about. One big one is security risk.
Like breaking encryption.
Precisely. Quantum algorithms like Shor's algorithm, which is brilliant at factoring large numbers, could potentially break the encryption we rely on today. That threatens data security, financial systems, everything. It means we urgently need new quantum-resistant standards.
That's a huge undertaking. What else?
Another concern is about accessibility and inequality. There's a real risk that the huge benefits of this tech could end up being unevenly distributed, making existing social and economic gaps even wider.
If only certain countries or companies have access.
Exactly. So Neven has been a strong advocate for responsible use, for embedding ethical principles right into the development process from day one, making sure these powerful tools actually serve the greater good.
It sounds like his influence goes way beyond just the technical side then.
Oh, absolutely. He's seen as an inspiring leader, a mentor, a community builder on a global scale. He's received major international awards, the ACM Prize, Fellowship of the American Physical Society, Nature's Innovator of the Year. Real recognition.
And his work has influenced policy.
Yes, things like the National Quantum Initiative in the U.S. Plus, he spurred the creation of open source tools like Circ for quantum computing.
Making the field more accessible.
Right, lowering the barrier to entry for researchers everywhere.
Okay, so let's try and bring this all together. Hartmut Neven's contributions. They're just immense, aren't they? From that foundational work in computer vision, the Neven algorithm, all the way to leading Google quantum AI, demonstrating quantum supremacy. His ability to connect deep science with practical application is just remarkable.
Truly remarkable. And his legacy is undeniable. His work really marked a turning point in computing. It inspired this wave of global investment, and it really cemented this essential interdisciplinary approach. You need physics, computer science, engineering, everyone talking. His collaborative model, bringing diverse experts together, that really stands as a blueprint for tackling the biggest scientific challenges ahead.
So here's a final thought for you, our listener. Consider how Hartmut Neven's vision of quantum computers as universal problem solvers might not just replace classical computers, but profoundly complement them. Opening doors to solutions for massive global challenges, think climate change, pandemics, resource scarcity, things that seem almost unthinkable to solve right now. What new problems will you dare to tackle knowing these kinds of tools are emerging? Thank you so much for joining us on this deep dive. Just a reminder that our discussion today was inspired by and based on that insightful essay written by Yergo Schneeppot. Until next time, keep exploring. And for more information, you can always visit schneeppot.de.